Hi everyone, welcome along to Children's University's fourth weekly lecture. This week's lecture is called Matter Matters. It's still got a bit of a science theme, but it's different to the last couple where we've spoken about physics and biology. Today's lecture is going to take us into the world of chemistry as we discuss the different states of matter. Now, for those of you who are watching this looking to get time into your Children's University Passport to Learning, there will be a quiz that will be available on the Children's University website or on the portal, which you'll be able to complete. You can then either submit it on the portal or you can print it out, fill the answers in, and take that to your in-school CUA coordinator to get the hours in your passport. This lecture plus the activity will be worth about 30 minutes for you. So you might be wondering, well, what is matter and how do I know where it is and when do I see it? Well, matter is everywhere. Matter is everywhere and matter is everything. Officially, in science terms, matter is defined as anything that has a weight and takes up space. Now that means it could be as large as the biggest star in our entire universe or as small as a microscopic atom. So there's no real range. As long as it takes up space and it has some sort of weight, it is a matter. Now, there are numerous different states of matter, and we're not going to talk about all of them today. Some of them are called intermediates. They're sort of halfway points between some of the ones we'll discuss. We will talk about the big three, those that are most visible and probably the ones that you're most familiar with, and that is solid, liquids, and gases. So you may be asking, well, why do we have three different states of matter? And that's all down to the particles and their bonds. Now, if you haven't already learned about bonds, a bond is effectively, well, it's something that holds two particles together. You could have very, very strong bonds, or you could have very, very weak bonds. And it's the amount of these bonds, the strength of these bonds, and also the density of the particles in the matter, which will determine if it's a solid, a liquid, or a gas. Now, as a bit of a way to help me understand it, I like to think about it as different strength jails. Really, really strong bonds that are tightly packed together, that makes for a really, really strong jail, and that's a solid. If we have medium strength bonds with medium packedness, or I guess medium density of particles, that would be a liquid. And a really, really weak jail with really, really weak bonds, for me, that's a really, really weak jail, and that's what we call our gases. We'll start off talking about solids, the really, really strong jails. Now, solids are made up of very, very densely packed atoms or particles. That means they're all very, very close together. They're also held together by incredibly strong bonds. So like I said, that really, really strong jail. So they can't move. Once they're held together, those bonds are so strong, the atoms or particles, they're not able to move around at all. Now, this means that solids aren't able to change their shape, and you're not able to run an object through a solid. So if you're interacting with a solid right now as you watch this on your computer or on a tablet or a mobile, whatever you might be using, it is a solid object. You aren't able to run your finger or your hand or anything through that object unless you go ahead and you break it. So that's the unique thing about solids, is they don't change their shape and you can't run an object through them unless you break them. So solids are the strongest types of jail, the strongest bonds, the particles are packed tightly together, and you can't run anything through them. Now, that doesn't mean there can't be different types of solids. I mean, cars, every time you get in a car made of different metals and things, those are all solids. An elephant, any type of animal or human being or fish, anything like that, even though they're very different to a car, they're all still solids because they hold their shape and you can't run anything through them without damaging them. And finally, other organic matter, like trees, plants, pencils made out of wood, once again held together by very, very, very strong bonds. The particles or atoms are very tightly packed together, and that means that they are solids as well. So moving along to our second state of matter, those are the liquids and the medium strength jail we talked about before. These are atoms or particles that are held together by average strength bonds, and they've got more space between them. If you look at the diagram on the slide in front of you, you can see that the blue atoms, they're still close together, but there is more space. They're not quite as closely packed as we saw in the solid. And that extra space means that unlike solids, you can actually pass an object through a liquid. You've probably done it when you've put a straw into a drink, or if you've used a paddle on a canoe or something like that. You can actually pass an object through a liquid, and that's because there's more space between the atoms and the bonds aren't as strong. Because their bonds aren't as strong, there's also some more flexibility. So it means the liquids are able to change their shape. So again, like we talked about with the solid, the only way for it to change its shape is to actually break the solid. You can't change the shape of your computer without breaking it. Liquids, they can change their shape depending on the container they're held in because they've got more flexibility between their bonds. And we can see some examples of that here. Oh no, those are the cats, who are also seen to be very, very good at changing their shape to suit their containers. Not because they're liquids though, just because they have some extra fluffy fur, which means they're able to take up or look like they're taking up many different shapes. No, for liquids, we can see examples of it in things like a glass. So if you put a liquid into a glass and then into a different glass, depending on the shape of that glass, the liquid will take that shape. You can see it in lava lamps, like you see on the right-hand side. So again, it's taking up a different shape there so it fits in the lava lamp. But we also see it when we do things even in raindrops. Down the bottom, you see the raindrops a little bit thicker as it falls from the sky, and that's because that gravity is pulling just a little bit more of that water downwards, and that's why it takes up that shape. So liquids, the medium strength bonds, more space between them, able to have an object pass through them, and they're able to take up the shape of the container in which they're held, which makes them probably more similar to a gas than the last state of matter that we have. And like I said before, this is probably the weakest jail of all. It's probably not even a jail. It's probably just like a fence around someone that's trying to keep them in place. So the gases have very weak bonds, and there's lots and lots of space between the atoms or the particles that make up that substance. They're not very dense whatsoever. Now, because they have weak bonds and a very, very low density, it's very easy for an object to pass it is a liquid. Now, you have evidence of that because when you run your hand through water, you can actually feel the water, while if you move your hand through the air, you might not actually feel the air at all. And that's just because there's less particles bumping into your hand for you to be able to feel. Like liquids though, because they have that flexibility, gases are able to take up the shape of the container in which they are held. You may not be able to see them, but we still know that we'll feel them sometimes. We still know they're there. We see the way they interact with our environment. So gases, we see the way that wind is able to move around windmills, things like that. We see gases released in the form of steam from steam engines, and we see the gas in the clouds too. Although in our clouds, we do have liquid as well, and that's a liquid that falls down. But through wind's behavior with other physical objects or chemical reactions, we know that gases exist, even though we can't always feel them or see them. So we've got those three states of matter, but the question now would be, well, once you're in a state of matter, are you stuck there forever? And the answer is quite simply no. Substances are able to move between their three states of matter. And the most obvious example that we can all think of, I think, is ice or water vapor. That is water in its natural form. Water exists as a liquid. Yet, if we reduce the temperature, it goes into ice and becomes a solid. If we increase the temperature, it turns into a gas and becomes water vapor. Now, the reason this happens is because of the energy that either breaks down or allows the bonds to reform. So when we add energy to a substance, so let's say we add energy to ice, that energy breaks down the bonds between the particles. And so what used to be lots and lots of strong and dense bonds, we have weaker bonds that aren't so dense. And that means the ice turns into a liquid, which is its water form. If we keep adding energy to that, we break down even more of the bonds. There's even fewer, so the density reduces once again, and the bonds are weaker, so they turn into a gas, and that is water vapor. So we can change the state of an object by adding heat. I guess in this form we use heat because that's the energy form that we use to break down the bonds. We can also go the other way by removing energy. So in this example again, by removing heat. So if we have a glass of water and we want to freeze it, we put it into a freezer where the heat that might be in the water is lost to the environment, which means with more heat removed and more energy removed, more of those bonds are able to form once again, and therefore the liquid turns into a solid because the particles have acted upon by more bonds and they get held together at a greater density. You might also have seen an example of this if you pour yourself a nice cold glass of water, usually in a glass made out of glass. If you put a really cold chilled water inside, you might see condensation forming on the outside. And that's the water vapor from the air coming into contact with that really, really cold surface, and the bond's starting to reform, and so the water vapor turns into liquid water on the outside of your glass. It's not like the glass is leaking. That condensation on the outside of your glass, that comes about because of the energy that's being removed from the water vapor. So, and this is where we come across things like our melting points, our boiling points, our freezing points, and our condensation points. And all substances have these. Some of them might just be a lot greater. So something like we can melt down metals, but it takes a lot more energy to turn a metal from a solid to a liquid because it's got much stronger bonds, and so it takes much more energy to break those bonds. And that's why the melting point for iron, for example, is much, much higher than the melting point for water. So the greater the strength of a bond, the higher the melting point, and that sort of thing there. Now, I just want to do a quick little demonstration. We've talked about water, but I want to do another demonstration using heat to show you how we can move between two states of matter. I've chosen to use candle wax for this one. And just as a bit of a warning before we do this, this is purely a demonstration because we are using a candle and some hot wax. I don't want anyone to be doing this at home. Just watch the video here, watch what I'm doing there. Certainly not an activity you should be repeating on your own. Okay, let's start the demonstration.
So we know that there are three states of matter, and we know that we can move between those states of matter by adding energy or removing energy. So I just wanted to use an example today that you've probably all seen before, but perhaps never considered as an example of a compound moving between its two states of matter. So the compound we're talking about today is wax, candle wax. So just this white substance you can see that surrounds the wick, that keeps it upright. Some of it can be centered, that's quite popular. But it is, at the moment, it's in its solid form. So if we press on it, it's not breaking. We know that a solid means we can't sort of move anything through it. We can't push through it. And right now you can't see that, and nothing's coming off either. So it's in its solid form. So all we need to do to break down those bonds and get it to move from its solid to its liquid form is to add energy to it. And we'll do that simply by lighting the wick. So as we light the wick is providing a fuel source for the fire. And so that candle itself is now, you can see it's lighting up. And what it's doing, it's releasing heat and heat energy into the immediate environment. If I put my hand around here, I can feel it a little bit. We're not so worried about the heat that's escaping. We're looking more so about what that heat energy is doing to the environment immediately around the wick. You can see now that the candle is fully established. And that means shortly it's releasing energy, and that will be breaking down those bonds in the candle wax around it. So if I just step back a bit, have a bit of a look, you can't see it's changing just yet. It's not going to happen right away. The melting point of candle wax is, I think it was about 60 odd degrees Celsius, and it might be different for different candles. So we've just got to wait a little bit, wait for that wick to burn. Wait for enough energy or wait for the candle to release enough energy to bring the candle wax up to its melting point, and then we can see it change its matter. So the candle's been burning for about 20 minutes now, so I'm just going to blow it out and we can have a look at what 20 minutes of heat energy has done to the solid of the wax. So I just extinguish it quickly, remove some of the smoke. Obviously that's still going to be there for a little while. But if you have a look, if I start to move it around now, you can see that top layer of wax is now quite clearly a liquid. So enough heat energy was released by the candle's wick to break down the bonds and convert the wax from a solid into a liquid. We can also tell it's a liquid because I can now, if I put my finger in it, I can move it through. So we learnt before that a solid, you can't move your finger or any other object through because the bonds are too strong. The particles are densely packed together. If I put my finger in here now in the liquid, we know that we can do that, and I'm able to quite easily move my finger through the liquid. because the particles aren't so close together and the bonds aren't as strong. Now, I wonder what's going to happen if I remove my finger from the liquid. What do you think will happen to the liquid wax that's obviously on my finger? Well, let's have a look and we can talk it through as I do it. So fingers in the liquid, I'm going to remove it from there. And we're just going to leave it for a little bit and try to have a think about what's happened. Now I can already feel the liquid starting to, I guess, harden. I can feel those bonds start to form again, and that's happening because in the liquid, where there was all that liquid there, that was still quite warm. That liquid itself had trapped quite a lot of heat energy, which meant those bonds couldn't form again. I've taken some liquid out of there. I've removed it away. It's got no source of heat anymore. And that heat that was in the liquid that's on my finger is now being released into the environment. As that heat is being released into the environment, the bonds in the wax are able to reform. And so slowly, the wax is going back from being a liquid into being a solid. Now I can blow on that with a bit of cool air to hopefully speed that up and get more of the heat out of, or more of the energy out from the wax. So I'm just going to do that quickly. Now it's probably going to take a little bit longer, but if you have a really close look there, we can see that just that bit there, it's obviously starting to firm up. what I'll do is I'll give it a few more seconds and I'll try to run my finger through it and we can see what happens. But I think what we'll likely see is as I push it over the top, try to run my finger through it, I'm actually going to move it because it's turned into a solid. So you can see it there. You can see that wax that's formed around. It's no longer moving. So if I move, it's not like flowing the way you'd expect a liquid to. And as I try to run my finger through it, oh, it's still cleared pretty well, but it's also gathered there. So we've still not quite a complete solid yet. There's obviously still some heat energy in there that's making it harder for the bonds to, making it harder for the particles to bond together to make a solid. But it's certainly not the free-flowing liquid we see down here. You know, that's even though we've taken the heat source away, it's obviously got enough heat stored in there that it's still able to, well, it's unable to bond back to make a solid. Around my finger, a little bit more again, and you're starting to see another example there. Now that we've pushed them away, is quite clearly a solid now around my finger. And if I were to leave that for another 5 minutes, I think it would probably go quite hard and come off a bit flaky, but I'm not going to make you sit there and watch wax dry.
So that concludes this week's lecture. I hope you enjoyed it. Now remember, if you do want to get the time in your Children's University passport, you do need to complete the activity that's downloadable off the website or on the portal. As with last week, if you do have any questions from anything that I've said today, you can put it in the comments section and we will do our very best to respond to you as quickly as we can. Furthermore, if you have any suggestions about some science topics that you would like us to cover in the future, you can also put them there below and we can try and discuss them as well. Okay, thanks very much and we'll see you again soon.